Okay, in this video, we're going to work a problem that falls into the category of particle equilibrium, which just means that for any free body diagram, we could model it as just a point because all of the forces on the body are concurrent, meet at that point. Okay, so cable ABC has a length of 5 meters. Determine the position X and the tension developed in ABC required for equilibrium of the 100 kilogram sack. So this is 100 kilograms. Neglect the size of the pulley at B. Okay, let's start. Let's identify a free body diagram that would help us here. So I'm going to separate kind of into space this portion of the rope right here. So this portion of the rope, right? So like there's a force acting right here. There's a force acting here, here, and they all kind of meet at a point, right? So that's valid. So again, this is particle equilibrium. Since all the forces meet at a point, we can just model that portion of the rope as a point, okay? And then let's put our the coordinate system, the origin of the coordinate system going through that point. So what forces are on this point? You've got a downward force, which is going to be equal to the weight of this sack, right? That's the weight of this sack goes through this rope here into this pulley, and so that's the weight of the sack, and the weight of the sack is 100 kilograms times 9.81, so 981 newtons. So 981 newtons. Okay, and then we've also got the tension in the rope here and here. Right, we know this is the same force. It has to be the same force. Okay, so let's call this, so this is T. Let's call this angle theta 1. Let's call this theta 2, and let's call this theta 3. Okay, so now let's go ahead and sum our forces about the X and the Y direction. So sum of the force is in the X must equal 0 because this is not moving. That piece of rope is not moving, piece of cable. So minus T cosine theta 1 plus T cosine theta 2 is equal to 0. We can divide through by T, and so what we end up getting is cosine theta 1 is equal to cosine theta 2. So this tells us that theta 1 is equal to theta 2. So let's just call this theta, and we'll readjust. We'll adjust the diagram here. And actually, let me rewrite these T's as well. So this is theta, and we've got T. Okay. So now let's sum the forces in the Y. So T sine theta plus T sine theta, so this is going to be 2T sine theta, right? Minus 981 is equal to 0. So 2T sine theta is equal to 981. So T sine theta is equal to 981 divided by 2. 490.5. Okay. So we don't have enough equations to solve for everything. So we're going to need to find another equation. So let's draw out this geometry and see what we can do with it. So we've got, okay, so we know this is three and a half. This is 0.75. We know that this is x. This is theta. And theta 3. And let's call this y. Okay, and this is, so A, B, C. Okay, so to get this extra equation that we need, most likely we're going to need to take advantage of this 5 meters here. We know that the length of AB plus the length of BC is 5 meters. So, I mean, let's write that down. We know that LAB plus LBC is equal to 5. This is most likely where our extra equation is going to come from. So LAB, what is LAB? Okay, well, we know that we can say this. We can say, so cosine of theta, right, is equal to the adjacent over hypotenuse, LAB. So there we go, right? We can say that LAB is equal to x over cosine theta, right? Okay, now similarly, we could say, so so this right here is this is 3.5 minus x. Okay, so cosine theta is equal to what? Adjacent over the hypotenuse. So that tells us that LBC is equal to right? So now let's substitute in to this equation here. So LAB okay, so these two bases are the same. So you get x plus 3.5 minus x. That's just 3.5 over cosine theta is equal to 5. So cosine theta is equal to 3.5 divided by 5. So, well, so this is equal to 0.7. So theta is equal to 45.6. Okay, they didn't ask for theta. They're asking for this x here. So we can't unfortunately, we can't come back to this equation, substitute theta, and solve for x, because x was like canceled out in this equation. We can solve for t though, so let's just we might need t, so let's do that. So t is equal to 490.5 over sine of theta. So 490.5 over so t is equal to so 686.5 newtons. So we still need another equation. So let's copy this. Okay, so let's see if we took the cosine of these angles. Let's see what the sine does for us. So okay, so here sine of theta is equal to what? So the opposite, this is what? So this is y minus 0.75. Well, we don't want to. Let's try tangent. So because we know that this x is very simple. We know this x very simply. So let's say, let's do tangent, right? So we get this y minus 0.75 over x, right? Because if we did LAB, we're trying to solve for LAB. That would be a lot more complicated. So this is a lot simpler. So okay, so now let's do tangent of this theta. This is equal to, so opposite over adjacent. Okay, and so we know theta. So all we need to do is just solve these equations for y and then set them equal to each other. And then since we know theta, we can just solve for x. So this equation, you multiply through by x. Yeah, so this would be y is equal to x tangent theta plus 0.75, right? And then this is y is equal to tangent theta (3.5 minus x). So if we set these to each other and then substitute in our theta, which is 45.6, so theta is equal to 45.6, then we can solve for x. So we've got what? X tangent 45.6 plus 0.75 is equal to tangent 45.6 okay, so tangent 1.0212, so 1.0212 x plus 0.75 Okay, so let's simplify. 1.0212x plus, so 1.0212 times 3.574 . Okay, so now let's add 1.0212 to both sides, and we get, so this times 2.0423, so 2.0423x plus 0.75 is equal to 3. Okay, so this 3.574 minus 0.75, 2.82408. Okay, so x is equal to 1.38 meters. Okay, and that is your x.